So thank you, and thank you for inviting me for giving a talk. It's a great pleasure to be in Vienna. So I'm going to talk about algebraic structures on non-crossing partitions. So I will first explain what are this sort of algebraic structure, double bialgebras. Maybe you're not very familiar with this, what they can give you as a structure, combinatorial stuff. And at the end, I will present some strange polynomials on non-crossing partitions, which I do not really understand. If you have some explanations, or if you've already seen this, I will be very interested to talk about them. So for me, what are non-crossing partitions? These are just this sort of diagrams, something like this. I'm not from the Coxeter world. I'm coming from literary and of algebras. So for me, it just will be combinatorial stuff without any Coxeter meanings. So these are really partitions which are represented by blocks with legs, and they are non-crossing. So we have here non-crossing partition with 1, 2, 3, and 4. So the structure I will put on them is a double bialgebra structure. So what is a double bialgebra? I start with a bialgebra. So to understand what it is, you can start with an algebraic monoid. You can think of an algebraic group, for example. Here I do not require to have the inverse. So what means algebraic? This is a monoid with a specific topology which allows you to define polynomial functions on your monoid. This is quite a specific topology, and you have an algebra of polynomial functions on your monoid. So proto means that maybe these are not finite dimensional objects. So you will have some complication of infinite dimensional meaning and so on, but it does not really matter here. So with this topology, you have an algebra of polynomial functions, but this algebra only reflects the topology. In this algebra, you do not see anything of the group structure, of the monoid structure. So to see this, what you can do is something like this. You can define a coproduct. In fact, if you have a polynomial function on the group, you can transform it into a polynomial function on G times J, just by this formula. So this is a polynomial function on J, and delta F is a polynomial function on G times J. And if your topology is well defined, this is really a polynomial function. And in fact, this belongs to this, and this can be identified with a tensor product of Cj times Cj. All this identification works because of the topology. So in fact, a bialgebra is an algebra with a coproduct, which is an algebra morphism from Cj to Cj tensor Cj, with good compatibilities. This would be co-associative and so on. I will explain this later. Yes? I will give you some examples later. You can fix of C. I work on C with addition of the multiplication. Then C of J is just the polynomial function C of X with one indeterminate. And Cx tensor Cx is identified with Cxy, which is the polynomial function on C times C. This is the simple examples. I will give you more complicated examples after. So this gives you a bialgebra. And if you have a bialgebra, you have a monoid considering the characters. If you have an algebra, you can consider all algebra morphism from B to C. This gives you a group. And if you have a set, sorry, this is just a set. But if you have a coproduct, this set is given a convolution product by this formula, and this becomes a monoid. So if you have an algebraic monoid, you have a bialgebra. And if we have a bialgebra, you have a monoid. And if everything works, the monoid of the bialgebra should give you the monoid which you started. Sorry? No, it's just an algebra morphism. That's all. Yes, compatible with the product. Only with the product, not the coproduct or anything else. In fact, if you want to be compatible with the coproduct, we'll obtain just one character, the unit. It's not really interesting. just compatible with the product and the unit, nothing with the coproduct. The coproduct appears here to define the convolution. So in fact, the set of characters does not depend on the coproduct, only on the product. So if your proto-algebraic monoid is a group, you have something more, which is an inverse, so a map from G to J, which is the inverse, and you can transform it into a map from Cj to Cj, which is called the antipode. If you take a polynomial function, you obtain another polynomial function, which is the evaluation of x, not in x, but x minus 1. And if everything is okay, this should give you really a polynomial function. And this is called the antipode of C of J. And what is called a Hopf algebra is a bialgebra with an antipode. And you can prove that this antipode has properties, interesting properties. You know that for the group, the inverse is an antimorphism of group. The same for the antipode. You can prove that it is, for example, an algebra antimorphism and a coalgebra antimorphism. So if you take a Hopf algebra, so this means a bialgebra with an antipode, then you can prove that the monoid of character is in fact a group. So I will have more structure on the monoid. In fact, it can be a group, or not a group, but a ring, for example. So it has two products, an addition and a multiplication, with properties. So what I will assume is that it has two products. Well, maybe products is not the good term, an addition and a multiplication. Both should be associative and unitary with units, 0 and 1. It's not really surprising. The multiplication should be distributive on the addition. I assume only on the right. So I just assume this. In fact, I will not have it on the left, only on the right. And I do not need that the multiplication and the addition are commutative. This is what I assume to obtain a double bialgebra. What can I do for this? Oh, I will have example what is a ring, but here it's not a ring because it's not left distributive. Maybe it's a half ring. I'm not sure there is a name for this. In fact, it's really pathologic in general. For example, you can think of formal series with a multiplication and the composition. You have a right distributivity on the composition and multiplication, but not a left distributivity. This is something like this, in fact. Not addition and multiplication, but maybe multiplication and composition, something like this. So I take the algebra of the monoid with two products. Well, you need to have some conditions so that the two coproducts are well defined. The addition should be polynomials and something like this. So you obtain two coproducts, one corresponding to the addition and one corresponding to the multiplication, big delta and small delta. Both should be algebra morphism. Both should be co-associative. So what does that mean? What's the way to understand a coproduct? If you have a product, you can take two elements of your algebra and you obtain only one element of the algebra. The coproduct is the dual notion. You take an element of your algebra and you can cut it into two parts, maybe into several ways. If you want to cut an element into three parts, you have two ways to do this. First, you cut it into two parts, one on the left, one on the right. You can cut the left part or the right part. And this should give you the same thing. So the same for big delta and small delta. There is a dual notion of a unit. So what is a co-unit? In fact, this is a linear form on B. With this compatibility, so what does it mean? You take an element of B, you cut it into two parts, a left and a right. You kill the left part by applying a linear form. It transforms your element into a scalar. So this is just an element of B. What does it mean? That you cut it into two parts, you kill the left part with the co-unit, and you obtain the element. You started this on the left or on the right. So you have a co-unit for big delta and a co-unit for small delta. So this just reflects that addition and multiplication are associative and with a unit. The most complicated thing is how to translate the right distributivity of multiplication and addition. this is reflected by this map. So what does it mean? You cut it according to the multiplication, then you cut the left part with the addition. This corresponds to cut by the addition, then both sides on the multiplication, and then you regroup together with this product the two right parts. This is exactly this sort of thing usually. See, you cut it an addition, two multiplication, and the appears twice. This is really the translation of the left distributivity. So this is what is a double bialgebra. I'm going to give a simple example of maybe the simpler example, simpler possible example, except C itself, which is not really interesting. So you consider this as a ring. So it has left distributivity and everything you want. This is a ring. So the polynomial ring on J is just C of X, the polynomial with one indeterminate. And X is to be understood as the identity of C, as a map from C to C. So with the two coproducts, so what does it mean? In fact, if you want to coproduct delta of xn, you have to compute xn into x plus y. You have to compute x plus y to the power n. You apply the binomial formula, you will find some monomials with xk times yn minus k, and you translate it into cx tensor cx. The same for this. If you want to compute the coproduct of x to the power n, you have to compute xy to the power n. This is xn yn. So this gives you this formula. And you have two co-units. The unit of plus is 0. The unit of times is 1. Well, so the co-unit is the evaluation in 0, and the co-unit for small delta is the evaluation in 1. So this is a double bialgebra. It is not difficult to show that this is co-associative and this is co-associative. Maybe if you want to compute it, the most difficult part is to prove this compatibility. So just a remark, you can simplify this formula. You know that delta and big delta and small delta are multiplicative. So you do not need to write all this. You just have to give them on the generators on X. This is simple. In particular, if you want to show that delta is co-associative, it is enough to prove it on X. You have to apply delta on the left or on the right. Most for small delta, and we'll see it's very simple. Okay. So now we change our point of view. I started with monoid, and I looked at the double bialgebra which was associated with it. Now it's different. Now you will have some double bialgebra. You start with a double bialgebra. So you will know that you have a monoid, which will be the characters of the monoid, but at the starting point, you don't have the monoid, but the double bialgebra. So this is an example based on graphs. So you take a vector space which has for basis the set of all finite graphs. So this is a formal space with a lot of indeterminates. And there is a very simple product, which is the disjunct union of graphs. The product is very simple. The unit is the empty graph, the graph with no vertex and no edge. You want to define two coproducts, so you want to cut a graph into two parts. The first part is very simple. If you take a graph, you can separate the vertices into two parts. One you put on the left, one you put on the right. Yes? No, they are unlabeled. In fact, this has isomorphism classes of graphs. I'm going to consider it. So for example, for this, so let's say for this, I can put all the three vertices on the left and nothing on the right, or everything on the right, nothing on the left. Or I can put these two vertices on the left. We'll obtain something like this, and the other vertex on the right, or these two vertices on the left. This gives the same term, so you have a coefficient 2. Or I can put these two vertices on the left or on the right. The first product is just separating the vertices into two parts. Very simple. It's very easy to see that it is co-associative. It's co-commutative. If you flip left and right, it gives you the same thing. The second coproduct is more complicated. In fact, on the left, you are going to contract some subgraphs. So for example, sorry? Yes, this is 2 to the power the number of vertices. For the second one, it's more complicated. You can see the number of terms is not the same in both. In fact, what you are doing, you are going to contract some subgraphs, which should be connected. So for example, for this, I can contract this subgraph on this, or I can contract everything, or I can contract this sort of thing. So I'm just going to contract some subgraphs which I set into a bubble. So for example, if I contract everything, what I will obtain is this. And on the right, I put the bubble, something like this. For this one, if I contract this and contract this bubble, what I obtain is a graph with 2 vertices. And the bubbles are this and this. This gives you a graph which is not connected. The same for this. So you have a coefficient 2. And for this one, I do not contract anything, so I obtain the graph. And the bubbles are just the 3 vertices. So this gives you a graph with 3 vertices, which is totally disconnected. This is also co-associative. This is not so difficult to see. It is compatible with the first coproduct. So what does it mean? To prove this strange relation, what does it mean? You first doing this coproduct, so you contract on the left, and then you cut the left part with the right part on the left part. So you apply the big delta on the left part, on the contraction. So this is the same as first cutting your graph into 2 parts, and then contract into the first part and the second part some subgraphs. Combinatorics is quite clear. You have to pay a little bit attention, but more or less it works. So another example, which is maybe the first one, which really appears, which is based on rooted trees. So the algebra is quite famous. It first appears really in a paper from Kohn and Kramer, which subject was the quantum field theory. In fact, for this sort of physical stuff, they needed a algebra, which was based on Feynman graphs, and they had a simple model which was based on rooted trees. It turns out that, in fact, this algebra was already known, but not totally on this form. It appeared in a paper by Butcher, maybe in the 60s, where he described a group structure on Rugel-Kutta method. The problem is that Butcher didn't know the formalism of algebras. So he worked with formal series of trees and really complicated to understand, but in fact, it is the same object. So it was at the end of the 20th century. Maybe 10 years later, Damien Calac, Kourouche, and Dominique Manchon defined another product on these algebras, and it turns out that it was maybe the first combinatorial example of double bialgebra. So it is based on rooted trees. So rooted trees is just a tree, a graph without any loops, with a root which I put on the bottom. So for example, these graphs are equal, but not as rooted trees. For the first coproduct, I cut some branches of the tree. Yes? No, there's not planar at all. It exists in a planar version, which is not commutative. This is commutative, and in this setting, these are the same, planar planar. For the first product, I just cut some branches, which falls on the right, and the trunk remains, which is on the left. So for this, I didn't cut anything. I cut everything. I cut a leaf, this one or this one, so this gives a coefficient 2, or I cut the 2 leaves. This gives this tree and this forest. For this, I do not cut anything. I cut everything. I cut the leaf, or I cut this edge, I obtain something like this. So this is the Kohn-Kreimer coproduct. So for the second one, in fact, I'm going to contract edges on the left, and on the right, this is the thing which I obtain when I delete the edges I have contracted. So for example, here, I did not contract any edge. So I delete all the edges, so I obtain a forest, totally disconnected. For this, I contract this edge or this edge. If I contract this edge, I obtain this tree. And if I delete one edge, I obtain something like this. And here, I contract every edges which now appears on the right. Yes? Yes. The Kohn-Kreimer coproduct on Feynman graphs is something like this. You contract on the left and you extract subgraphs on the right. This is something like this. But this coproduct on Feynman graphs is also related on this. In fact, they have some hidden Prelly structures, and this is the draw to the free pre-algebra. So in some sense, the Kohn-Kreimer coproduct is related, on Feynman graph is related to both of them. But the definition really looks something like this. But contracting subgraphs of Feynman graphs is much more complicated than contracting edges, which are quite easy, in fact. So now I'm coming back to non-crossing partition. I'm going to define two algebraic structures on non-crossing partitions. So I should mention that we have some motivation for this, which I do not really have time to explain. In fact, these algebraic structures comes from consideration in three probabilities. They can be used to organize the relation between moments or cumulants. And in fact, we talked about them yesterday, I think in the question for Daniel. He mentioned that there, for example, to compute the inverse of a character, which was related to Hopf algebraic structure, this is one of this one I'm going to present. So what I'm going to do, I'm going to take a polynomial algebra generated by all non-crossing partitions. So there is a first complication. I'm going to consider monoid of non-crossing partition. So I will need a symbol for the product of this algebra, which is symbolized by a dot. So this is not a non-crossing partition. This is a product of two non-crossing partitions with one block of size 1. So this is different of this. So these two non-crossing partitions are different, of course. This is a non-crossing partition. This is a product of two non-crossing partitions, so this is different. The same for this. And the product is commutative. So with a dot, everything commutes. And there is a unit, which is a formal unit, which has to be understood as a monomial with no non-crossing partitions. So the first coproduct is something similar to the Kohn-Kreimer coproduct. The first Kohn-Kreimer coproduct, I separate the blocks into two parts, one on the right, one on the left. Yes? No, this is something else. So you have the unit, non-crossing partition, products of two non-crossing partitions of 3, 4, and so on. Formal product. Yes, the symmetric power. A symmetric power, not a symmetric algebra on non-crossing partition. I want it to be commutative. In fact, non-commutative, it won't work. You can prove that if you have a double bialgebra, it's always commutative. So you have to take commutative. So it is a symmetric algebra in non-crossing partition, if you want to. Or a polynomial algebra, which indeterminates are non-crossing partitions. So for the first coproduct, I separate the blocks into two parts, one on the left, one on the right, and I respect the nesting. So for example, if you have a situation like this, if I choose to put this block on the right, the block which is nested in it should be also on the right. So I respect in this way the nesting structure of the blocks. So for example, for this, I can put all the blocks on the left or all the blocks on the right, okay. or I can put this block on the right and this block on the left, but I cannot put this on the right and this on the left. This is not possible. For this, it's a little bit more subtle. There is no nesting, so I can choose to put everything on the left or on the right. For example, this. I can choose to put these two blocks on the right, these two blocks on the right, or these two blocks on the right. So for this, they are neighbors. They are not separated by any other blocks. So this will give you something like this. For this, it's much more complicated because they are separated by another block. So you have to cut the two blocks into a product. So this is why there is a dot here. This is quite subtle, but this is really important for the relation between moment and cumulants. So in fact, sometimes, if I separate the blocks, I can obtain some products on the right, and sometimes just a non-crossing partition. It depends if the blocks are separated by another blocks or not. Yes. This is really different. And in fact, here on the left, you have only non-crossing partition or one. And on the left, you can obtain products. So this is really totally disymmetric. Left and right are very different. It's not co-commutative at all. Sometimes yes. I have to split it if they are separated by another block. If they are not separated by another block, I put them together. It depends. There is a co-unit, very simple, which is this. On all non-crossing partition, this is equal to 0. So for example, if I apply this on the left of this is 0, this is 1. The co-unit is an algebra morphism, so it remains this, 0, 0. What remains is only this thing, which is the first initial non-crossing partition. So this is very simple to see that this is a co-unit. For the second one, what I do on the left is that I do the fusion or the melting, I don't know how to say this, of several blocks. But of course, if I do this, the blocks, the partition I obtain should be a non-crossing partition. So for example, for this, I did not fusion any blocks, so I obtain this on the left. I fusion these two blocks, and what I obtain is something like this. On the right, the blocks here are this and this, so I put something like this with a dot. And the blocks I fusion are the two blocks, which gives something like this. For this one, it's more complicated. In fact, I can do all the fusions I want, and I will obtain all 5 non-crossing partitions with 3 legs. For this, I did not fusion any blocks, so I obtain the products of 2 blocks, of the 3 blocks. Here, I take the fusions of 2 blocks, for example, the first and the second, this gives you the first, the second and the third, the first and the third. And in each time, what remains on the right is the block alone and the 2 blocks I fusion. And here, I fusion the 3 blocks together. I think there are the fundamentals for what I want to do, at least. There are other ones. For example, you can say that all non-crossing partitions are primitive. P tensor 1 plus 1 tensor P. It exists. I think it's more or less useless, but why not? But I'm not sure. There are also structure on permutations. I did not check, but I think that this is really something different. This is, I'm not sure. Yes, the nesting is very important. In fact, it's fundamental for what I want to do. There are op algebra of permutation, a lot, in fact, of op algebra of permutations. I'm not sure that there is a good morphism from non-crossing partition to permutations, which satisfy the compatibility with the product and the coproducts. I don't know, but I don't think so. So there is a co-unit, which is one if the non-crossing partition has only one block and zero otherwise. And this is a double bialgebra. It's quite a combinatorial stuff to satisfy, but okay, everything works. So now, what can you do if you have a double bialgebra? I'm going to present some results. So first, maybe you want to compare it with another bialgebra. So you're interested in the first coproduct, in fact, and in the product. So you want to compare this with another bialgebra. So this means that you want to find some morphism from Bm delta to something else, B prime, M prime, delta prime. This gives you a set of bialgebra morphism. And in fact, on this set, a monoid of characters associated to the second coproduct acts with this simple formula. So this is a Hopf algebra morphism for the first coproduct. This is a character. You can transform it into another bialgebra morphism by the action like this. So this means that if you have a Hopf algebra morphism, in fact, you have a lot of them. You can deform them, with the action of any character. In fact, in this bialgebra, there is a lot of characters. Yes. So phi is a morphism, lambda is a character. It acts on the right. You have to do a choice at a point. You have a left or right. I choose the right distributivity. So this is the right action. You can everything on the left also. I choose right. I don't know exactly why, but I choose right. So a special example of double bialgebra is the first one I gave, which is the polynomial algebra. In fact, under a condition of connectivity, I will detail after, there is a unique bialgebra morphism from B to C of X, which is compatible with the product on both coproducts, on only one. So this means that this phi1 is a very special morphism from B to C of X. This is the unique which is compatible with all the structure. Moreover, if you have phi1, you obtain all morphism for the first coproduct just by the action of lambda, of characters. In fact, if you make the monoid of character acts on phi1, you obtain all morphism, all bialgebra morphism for the first coproduct from B to C of X in a bijective way. The action gives you no morphism, and you obtain all in a unique way, and the inverse bijection is just take your morphism for C of X and evaluate it into 1. And these are two bijections. So this element here will be called polynomial invariance, and this one, which is quite special, will be called the fundamental polynomial invariant. So this is the set of bialgebra morphism from B to C of X for the first coproduct, only the first coproduct. For the second coproduct, there is only one, so you don't need a notation of set for this. So, okay, but how can you compute phi1 with this formula? What does it mean? You have a coproduct. The reduced coproduct is just forgetting the primitive part, x tensor 1 minus 1 tensor x. Maybe you observe that for non-crossing partition, for the first coproduct, you always have a primitive part, which has this part here. You forget it, and this is still co-associative. So you can iterate it, delta tilde cut into 2 parts, delta T2 into 3 parts, and so on. So you cut your X into all possible parts, forgetting the trivial parts. You apply the co-unit of small delta on the all parts. This gives you a scalar, which you multiply by the Hilbert polynomial. You can observe that this is an infinite sum. The connectivity condition means that this, in fact, goes to 0 if n is large enough. The connectivity condition just means that this sum is in fact finite when applied to any x. This is the connectivity condition you have. Okay. So you can apply it to graphs. So I describe a double bialgebra structure for graph, which is connected, no problem. So this means that you have a unique polynomial invariant, fundamental. And in fact, if you compute it, this is just the chromatic polynomial. Well, it's not really surprising. If you look at graph theory, you know that the chromatic polynomial is very important for this theory. And in fact, you characterize it as a unique double bialgebra morphism for these two coproducts. Yes? Yes. Yes, in fact, this is the way you obtain it. This is cutting the graphs into n parts. So this is in fact a coloration of the graphs. Yes. In fact, this reduced coproduct is just cutting the graph into two non-trivial parts, three non-trivial parts, and so on. This means you do some coloration in some sense. Coloration. Yes. You can, yes, in some sense. In some sense. So for router tree, if you do this, what you obtain is something like this. You count maps from the vertices to n, so that if you have an edge, so the edge oriented from the root to the leaf, then you should increase. So in fact, these are quite well-known polynomials. These are Erhard polynomials. Usually they are not defined on trees, but rather on polytopes. But if you have a tree, you can define a polytope. It's just inequalities, and what you obtain is the Erhard polynomial of the polytope associated to the tree. So this is quite well-known polynomials. More or less well-known polynomials, I should say. So another problem I mentioned is to compute the antipode. You know for algebraic reasons that for the first coproduct, your monoid of character is in fact a group. You have an antipode. And you can compute it with a formula which is called the Takeuchi's formula, which is rather similar to this, in fact. You have a sum of the iterated coproducts, but instead of applying characters, you multiply this together with a thing. Like this is just an inverse of the identity for the convolution. Well, at least it works, but it's not really convenient. I do a computation for instead of x explicitly. So for example, for this, you can cut x4 into one part, into two parts. There are three ways to do this with coefficient, binomial coefficient, 4, 6, 4, into three parts, 1, 2, 3 times, with coefficients 12, 12, 12, or into four parts, x, 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 with coefficient 24. Everything goes together, and at the end, you only obtain x4. This is just to show that the Takeuchi formula is not really useful, usually, because you have a lot of cancellations. All this computation to find x4, well, probably it's not a good idea to use this. Here you can do better if you have a double bialgebra. So in fact, what you have to do is to inverse only one character, the co-unit for the second coproduct. So you inverse the co-unit for the second coproduct for the convolution product associated to the first coproduct. You obtain something alpha, and if you have alpha, you obtain the antipode just by this. So you apply the coproduct, and then you kill the left part with this alpha. And you have a way to compute alpha if you know the fundamental polynomial invariant. In fact, you just evaluate the fundamental polynomial invariant into -1. And you obtain this formula for the antipode. So for graphs, if you remember what is phi1, this is the chromatic polynomial. It's not obvious what is the values of the chromatic polynomial in -1, but it's known. It's related to a number of orientations, acyclic orientations. But it's not so obvious to see it from the combinatorial stuff, from the algebraic stuff. So what is the fundamental invariant for the chromatic polynomial? Well, what you have to do is to iterate the coproduct. So the coproduct is separating the graphs, the non-crossing partition, the blocks into two parts, one on the left, one on the right. So this means that in fact, you apply a map F from P to N. So you index the blocks. The blocks by 1 will be the first part, the block by 2 in the second part, the block by n in the nth part. And you should respect the nesting conditions. So that means that B prime is nested into B. So it should be a B on a B prime, not a P on a P prime. So F should be increasing if you go up in the non-crossing partition. So this is the iterated coproduct. For the reduced iterated coproduct, you just kill the empty monomials. So you replace all F by surjective F. And then you apply the co-unit on all these parts. And the co-unit is 1 if this is a monomial of non-crossing partition with a single blocks and 0 otherwise. So this gives you an interpretation of a fundamental invariant for non-crossing partition. So this is something like this. You count, in fact. So this is a non-crossing partition. This is a polynomial attached to P. You apply it into N, where N is an integer. It counts something. It counts the number of maps from P, from the blocks to N, such that if B is nested, if B prime is nested in B, then F of B prime is greater than F of B. If two blocks have the same color, well, one is smaller than, they cannot be nested because of this condition. So one is on the left and the other is on the right. B is on the left, B prime is on the right by convention. Then they should be separated by another blocks, which I'll call B prime. So this is quite sort of error condition. This is much more stranger. So, okay, this is a combinatorial definition. You can compute it with sort of formula. What you can do is that you can prove is something like this. You take a non-crossing partition, P, you evaluate your polynomial in x plus 1. This is the same as this formula. So what does it mean? This is easy. The base of P are the elements which are the lower elements for the nesting relation, which are at the bottom of the non-crossing partition. You choose an element of the base, you delete it, and your non-crossing partition fall into 3 parts. What is on the left on your element B, what is on the right, and what is up B1, P1B, P2B, P3B. And this gives you a way to iteratively compute these elements. So how does this work? Here, think of the interpretation of this. This is a coloration of P, of the blocks of P with n plus 1 coloration. So you add a color which could be 0. Because of the increasing condition, if a block is colored by 0, it should be in the base because of the nesting condition. But of course, because of this condition, you cannot have 2 elements of the base which are colored by 0 because they should be separated by an element colored by something lesser than 0. You don't have something like this. So at most, there is one element of the base which is colored by 0 or 0. And that's gives it. I did not put the X here, yes, because, well, if I put X, it was too big. That's all. So this is the proof. And what you can compute is something like this. Just by induction. In fact, I did not made it by hand, but I asked Sage to do this with this formula. So can I take over 2 minutes? So I skip for the antipode. I was especially interested in the polynomial invariance phi1 applied when a non-crossing partition is restricted only to its base. So you don't have any nesting. For this, it just depends on the number of blocks. The size of blocks is not important for this, only the number of blocks. And you can compute these elements. You obtain something like this. So this is the first one. They turn out to be quite complicated. I don't not really understand them. So they just count the condition I gave before. But you have formulas for this. In fact, they are rated by something like this. You can consider this infinite matrix with binomial coefficients, and then you can prove that this series of coefficients is a vector. So we have to do the m to the power x in some sense of this vector, and this gives you this polynomial. In fact, this is the way I computed this stage. And this formula just comes from this. This is a transformation of this relation applied when you just have a base, in fact. So, another thing, these are polynomial. This polynomial just reflects some combinatorial stuff. So it is quite natural to develop them in the basis of Hilbert polynomials. And you can compute this number, you obtain something like this huge array. The diagonal is easy. That's the factorials. The other coefficients are quite mysterious. For example, I looked for this one in the OAIS. In fact, it does not appear anywhere. Quite strange. I don't know what exactly to say about this. It seems that it is easy. You can find formula for them according to the diagonals. So for this is the factorials. For the second diagonal, so this one, 0, 1, 10, 86, I managed to prove this formula with an harmonic sum. For the second diagonal, 0, 0, 4, 254, and so on, what you obtain is something like this. You obtain a rational fraction, a harmonic sum, and a double harmonic sum. And in fact, you can continue like this. What you will obtain is an expression with a factorial, harmonic iterated sums, and a rational fraction. Here are some references on archive. So the last one is very recent. I put it 2 weeks ago, maybe, on archive. And thank you very much for your attention.
Thank you, Loïc.
In fact, it's not the same. You don't have any morphism from non-crossing partition to rooted trees or planar rooted trees. This is different because of the dot. In fact, you could do something like this, but you have to not to take the algebra generated by trees, but by forests. You can do union of forests or a dot union of forests or something like this, which I did not do. This is really different, and you can see it because of these polynomials. These polynomials are not Erhard polynomials. They are something else. So this is not the combinatorics of trees. This is really something different. No, this is a failure. I try to understand the Cleverras complement into an algebraic way. I don't know what it is. I don't know if it is something. It is not compatible with the product. It is not compatible. The product is different because it's just a formal product. So it does not have real meaning. But it's not compatible with the coproduct, nor the first one, nor the second one. So I don't know what to do with the Cleverras complement in this setting. In fact, what we had was a formulas for the convolution of characters for cumulants or moments, something like this. We translate it dually in this coproduct. So the second coproduct at least really gives you the convolution formulas for moments or cumulants coming from 3 probabilities. I did not find anything, but maybe I did not look at the good place, or I did not work enough. Maybe that's the point. Yes. Yes, yes. Yes, in fact, what you can do for polynomials, you can also do for quasi-symmetric functions. So you obtain also a unique, homogeneous morphism of double bialgebra into QSIM. So this is quite the same. This is related to the same colorations. This is given by the same colorations. To each coloration, you associate a composition. The number of blocks with the first color, with the second color, and the last color. So to each such coloration, you associate composition, and this gives you a unique double bialgebra, homogeneous double bialgemorphism from non-crossing partition to quasi-symmetric functions. This is very close to polynomials, so I just talked about polynomials because long enough. No, because of the problem is this dot here. Without the dot, it would work. With the dot, it does not work. And you can see it at the end with the polynomials you obtain. Like this, for example. If this would be a morphism, this should be Erhard polynomials. And this is not a Erhard polynomial. The first one here, because you don't have any really nested problem, here you have a problem with the second condition of colorations, which is not a Erhard condition. So this is not a Erhard polynomial, so this indicates you cannot have any morphism from non-crossing partition to trees, which sends you a non-crossing partition to a tree or a forest, just because of this one.